Hello everyone, in this video we'll be commenting some imprecisions that I found in the user's guide of Chernobyl The Legacy Continues. So this video will be just PDF and I will talk over the PDF about the imprecisions that I found. And this video is motivated by Jimmy Midas one that asked me something about the pressure set point. So I came back to the manual just to check the pressures, but instead of going directly to the page where this is specified, I started reading the manual from the beginning. Why not? And in the section 2.0, I found several things that drove me mad. So I decided to make this video to clarify these problems. So section 2.0, entitled "The Worst Nuclear Accident in the History of the World," explains basically what happened in the night of the 26th of April 1986 with the reactor 4 exploding and so on. And then in the second paragraph, it says that this is because of several flaw design features of rbmk 1000 Soviet design. And then it goes point by point to specify what are these features that caused the accident. So I will go point by point, but tell you what I think is wrong here, or at least imprecise. Point number 1 says, they are refueled during operation. Other than the Canadian CANDU reactor design, no other reactors in the world do this thing. And at the end it says the rbmk 1000s were designed this way partially because they can be used in one stage of weapon-grade uranium enrichment. Well, this is not true. The fact that they can be refueled during operation is true, but they cannot be used in one stage of weapon-grade uranium enrichment. Uranium enrichment is done by physical means, either by centrifuge or by gas diffusion of uranium fluoride. I think it's fluoride, but I'm not really sure. I'm not a chemist. If you remember the problems with Iran in the previous years and the nuclear treaty, you know that Iran signed a treaty with the Obama administration in which they gave them some limits on the number, among other things, on the number of centrifuges that they could have to enrich uranium. So Iran used centrifuges to enrich uranium to power the nuclear power plants. Of course, they have the right to do because this is a civilian use of nuclear energy to produce electricity. So international community cannot forbid them from doing this. The problem is that mainly Israel was afraid that they were going to build nuclear bombs and maybe use them against them. So they pushed very hard. So the international community, led by US, imposed some restrictions to Iran so they could not enrich too much uranium. So the restriction was 120, if I remember it well, centrifuge machines. This, and with conjunction with several international supervisors or inspectors that were in place to make sure that they were not sneaking some of the enriched uranium to build a nuclear device like a bomb. So this was enough for several years of peace, and Iran could run nuclear energy for civil purposes, enriching uranium by themselves in their own centrifuge. But with the Trump administration, Trump said that this was an ashaming treaty or deal. Probably he was pushed by Israel. So he put back the sanctions to Iran because of using this 120 centrifuge, which according to Israel and to the Trump administration was too much. Why 120 centrifuge? Well, this is more or less the quantity of centrifuges that working full-time were needed to produce enriched uranium for their nuclear reactors. The problem at least from the point of view of Israel, is that if by some means they succeeded hiding from the international inspectors the use of this uranium, and they started stockpiling uranium aside from the civilian use, they only needed 12 months to reach the quantity that is needed for one nuclear bomb, which is somehow possible to do because the refueling intervals of classical reactors is 18 months. So by the time the international community could realize that they ran out of fuel for their nuclear reactors, they could already have had enough uranium to build a nuclear bomb. Well, this is just to explain you that weapons-grade uranium is done using centrifuge mainly. It's the main technology that all nations use to obtain this material. What they meant in this paragraph, what is it called in English? Paragraph, yes. What they meant in this point is not weapon-grade uranium enrichment, but weapon-grade plutonium breeding. And I will tell you why. Plutonium is an element that is not found naturally in our planet. And actually in the universe it's very rare, it's very difficult to find. Because it has one of the isotopes of plutonium that can be used to build nuclear weapons has a decay time or a half-life time of 200,000 years. I think it's more or less this number, I'm not really sure. This may seem a huge number, very long time, but in the scale of the universe it's very short. So it means all the plutonium that was created at some moment, maybe in the explosion of some supernova or some star, I don't really know where, already decayed away. So we don't find it in any significant amount anywhere in the universe. It could happen that some atom of uranium that can exist naturally in the universe by chance just captures a neutron that is the result of a alpha decay of some other radioactive particle in the universe, but this is so unlikely to happen that you just don't find plutonium in the universe. So the only way to obtain plutonium is in a nuclear reactor. And the way to obtain the plutonium that you need for a nuclear device, like a nuclear bomb, is to insert enriched uranium in a neutron-rich environment, like a reactor running at nominal power. And when uranium-238, which in principle is not a feasible material, but it's most of the uranium that we find in nature, when this isotope captures one neutron, it becomes plutonium-239, which is the desired element to build nuclear bombs. So you see, it's very easy. You just insert enriched uranium in a reactor. When it captures some neutrons, you have the fuel to build nuclear bombs. The problem is that if you don't withdraw this from the reactor at the right moment, after it captured the neutron, it will capture a second neutron and then it will become plutonium-240, which is a very undesirable material or isotope to be put in a nuclear bomb because it has a very short half-life. It means it's very hot, very radioactive, so it will damage the electronics of the bomb. And also it will make the bomb go critical very easily. So it's very difficult to detonate this kind of bombs that have a significant amount of plutonium-240. It's estimated that to build an implosion nuclear bomb, you need around 93% of plutonium-239 enrichment. So less than 7% of 240. Otherwise, you cannot build it successfully. So how to do this in a regular nuclear reactor? You insert the enriched uranium. You wait the optimal time, which happens to be around 12 months, and then you withdraw the fuel elements, and you have the optimal quantity of plutonium-239. This is not yet weapon grade. This is called reactor grade, and then it needs several more physical processes, or I don't know exactly what, to enrich it further in U-239. So this is what they meant here. This is used in one stage of weapon-grade plutonium breeding. And why the refueling during operation is important for that? What's this message? Yes, okay. So in a normal reactor, you refuel every 18 months, which doesn't coincide with the optimal time to withdraw the uranium to have the maximum quantity of plutonium-239. That's why if you run a reactor and you operate it to maximize the production of plutonium, you will not have the most economical possible reactor in terms of energy production. But because you need to stop the reactor every time you refuel it. But if you have a technology that allows you to extract some fuel elements, not all, just some fuel elements with the purpose to make plutonium without stopping the reactor, the plutonium production doesn't affect the economical viability of your reactors, which is very desirable. And secondly, in a context of non-proliferation, so in a context in which we are after since the end of the 50s, I think, in which all the countries signed an agreement not to build more nuclear weapons, or at least not to build too many. You don't really want the other countries to know that you are producing plutonium. You could create some international conflict. So if you stop your nuclear power plants every 12 months, everyone will realize, the grid controllers will realize you need like 1,000 workers to make the refueling, so everyone will know that you are producing plutonium. But if you have a rbmk design in which you don't need to stop, basically no one knows. You just have 5 workers that go to change one fuel assembly and send it to some military base, and no one knows that you are producing plutonium out of this reactor. So this is basically the change that it needs for this to be correct. Weapon-grade plutonium and breeding, not enrichment. Because what you are doing is to breed the plutonium. You create it from a fertile material, which is uranium-239 plus 1 neutron coming from some other fission. Okay, let's go to the next point. Point 2. Maybe I talk too much. What do you think? Point 2. For economic reasons, they use unenriched uranium for fuel. Without going into nuclear physics at this time, using unenriched uranium creates some challenging operating problems, one of which is the instability of the reactor to operate at reduced power ranges for any length of time. This phenomenon is called reactor poisoning. Well, this is a bit not very precise, because it's not the fact that you are using unenriched uranium that creates any problem. And reactor poisoning happens in all reactors. It happens in PWRs like AP1000, it happens in BWRs. So you can say because of the design of this reactor and because it's meant to have much more reactivity, so you don't need to enrich your fuel, the parameters like the time constant and the magnitude of the poisoning may be different, but it's not because you are using unenriched uranium that you have the consequence of having poisoning. So just a bit imprecise sentence, but anyway, the meaning is understandable. Point 3, I don't have any objections. Point 4, the control rods that stop the nuclear chain reaction use graphite water displacers on their tips. Since the reactor is moderated with graphite, this causes the reactor power to momentarily increase when the reactor is cramped. Okay, so in the way this is formulated, this sentence, since the reactor is moderated with graphite, etc., it seems that it's because it's a graphite moderated reactor that this happens, but this is not the case. Actually, if you input a water displacer made with graphite in any kind of reactor with thermal neutrons, you will create an increase of power. And even more than that, it's not because the displacers are made of graphite that they create a power increase. Actually, if you look at the geometry, when the control rods are totally withdrawn, the graphite displacer is geometrically symmetrical in the center of the core, with a gap in the top and in the bottom, which is still filled with water. When you start scramming, the bottom part of the reactor, the water is being substituted by graphite, and in the top, the contrary happens. The graphite is being substituted by water, until half second later when the absorber rod starts entering the reactor. So you see, at the very beginning of the movement of the control rods, the effect on reactivity is symmetrical. You are adding the same graphite in the bottom that you are withdrawing from the top. So if you don't take into account only other nonlinear effects, like the positive void coefficient, actually this would not create any increase of reactivity. So it's the geometry of the displacers plus the nonlinearity of other things that have nothing to do with the displacers, like the positive void coefficient, that altogether make this slightly increase of power during half second when you scram the reactor. And most importantly, it happens locally in the bottom, the higher increase of power, which accelerates the exponential growth of the positive feedback with voiding. So this sentence, since the reactor is moderated with graphite, it's not the reason why. It's not because it's moderated with graphite. Okay, we'll go to the point 5. And this is, I can say the other points are just imprecisions, little mistakes, but this, I would say it's wrong. It's better to erase this from the user manual because it's very wrong. The Soviet rbmk 1000 reactors do not use a containment structure. This alone would have greatly reduced the severity of the Chernobyl accident. American reactors are housed in pressure-sealed containment vessels designed to contain radioactive components in the event of an accident such as Chernobyl. These containment structures are expensive and significantly increase the construction time of a new plant. The Soviets made the decision to not house their reactors in a sealed containment vessel. Well, reading this, they make you think that the containment really can't take anything, but this is not true. The containment is only designed to withstand a local accident. And here, maybe in the other points you can say, I have no idea what I'm talking about, and you may be right. But in this, I know more or less what I'm talking about because I'm civil engineer and I know how to design this kind of structure. This concrete-made structure, heavily pre-stressed, which in the design criteria is not following the, I'm not sure how to say this in English. In structural design, you have two criteria for design. You have the ultimate limit state and the service limit state. I'm just translating this from Spanish, so I hope it makes some sense. The ultimate limit state is the one in which the structure fails because it reaches the compressive strength of the material or because it plastifies in some junctions, etc. And the service limit state is the one that the structure doesn't reach its structural resistance or strength limits, but because of the movement or the vibration or any kind of deformation that avoids the normal use of a structure, you are limited in the design because of this. So let's put some example. A concrete pile that holds the weight of a building. This is a typical case of ultimate limit state because it has a very high compression from the building and it needs to withstand this. So you will just divide by the weight by the area of this pile and be sure it's below the limits plus the security factors and everything. But imagine a very slender bridge for pedestrians, like the Millennial Bridge in London. This may be already okay for the ultimate limit state, but because of wind or because of the resonance with the walking of people, it may vibrate, and because it's very slender, it may move too much. So people will get sick or will fall down while walking through the bridge. So the criteria for this bridge will not be the ultimate, will be the service limit state. In a containment building of a nuclear power plant, it's very clearly that we are in a service limit state. This seems crazy, but actually what it's supposed to do, a concrete building, is to hold the pressure of steam in the case of a local accident. A local accident is a loss of cooling accident. So basically, your primary loops, some of them is broken, or the reactor vessel itself is broken. So you basically lose the coolant, and because the reactor is very hot, it boils because it's exposed to the atmospheric pressure. So it doesn't matter if we are in a BWR or a PWR, it will boil and it will increase the pressure inside the containment. So the containment must seal this from the atmosphere to avoid the release of radiation to the outside. So these buildings are more or less designed to withstand 0.5 bars, which is 500 kilopascal of pressure. That's why if you have ever seen the construction of one of these containment buildings, you will see that before putting the concrete, it's like a jail. It's like a nightmare of steel. There are so many ribs of steel that you cannot even see through. This is to make sure that the concrete has always compressive strength sealing all the fractures. So there is no possibility that gas or steam or radioactive particles go out through a LOCA during the event of a LOCA accident. So basically, the containment building in which here they are saying that could have avoided the Chernobyl accident, actually no. It cannot withstand any kind of explosion. A very small explosion can demolish it. An airplane crash will demolish it. So anything violent or dynamic is not made to withstand it. It will basically withstand 500 kilopascal of pressure. And I want to put an example that it's another real case. It's the case of 3 Mile Island nuclear power plant. I think the nuclear power plant was called Harrisburg. I'm not really sure. But it was a meltdown, happened in US much before Chernobyl. I don't really know what happened now, I don't remember, but it seems that they lost the ability to cool the core and it melted down. Because of the melting down, they lost the control of the primary circuit and there was a release of steam with a very high level of radioactivity to the containment building. So the containment did its job. It avoided the radioactivity to go to the atmosphere in a very first moment after the LOCA accident. And after days of the accident, while the reactor was destroyed, the nuclear power plant was inoperative. But they had all the radioactivity contained inside this building, which did very well its job. It contained the pressure that released the reactor with all the radioactivity. But what the operators did, and this is what it's driving me mad, what they did after a few days, they just open a valve and release this to atmosphere. So what's the point to have a containment building? If when you have all the radiation contained inside it, you just release it so you don't need to spend money in some HEPA filters or whatever needs to be done to clean it. It's crazy. So every time someone tells me that containment buildings can avoid nuclear disasters, I'm absolutely crazy because first, this is not true. They just contain the radiation emitted in a LOCA accident, and the only time actually it could have served to avoid an emission of radioactivity to the atmosphere, it was not used for that. So after the accident, they just release it anyway. So what's the point? So at the end here in this paragraph, they say the Soviets made the decision to not house their reactors in a sealed contained vessel. Well, it's not that easy like that. And it bothers me quite a lot, this paragraph, because it starts with some nationalism, like saying American reactors are housed in pressure-sealed containment. Yeah, we see how you used it in 3 Mile Island. And then say the Soviets made a decision not to house it. For me, this is too patriotic, sorry. If we look at the diagram of an rbmk, the rbmk is very different compared to a PWR reactor in the sense that it's huge. It's much taller, wider, and deeper. So building the containment, it's actually much more difficult and expensive than building it for a common nuclear power plant. So in this sense, I would say, yes, they decided not to build the containment, but it made sense. In particular, at that time, now it would be inadmissible anywhere in the world to build nuclear power plants without containment. But at that time, even the constructors of classic PWRs, many of them, they said, come on, we have so many safety measures that the containment is not really needed. We could save this money. So there were some voices saying that it was a waste of money to build such containments. So, I mean, now that the accident happened, we can say it was a mistake, but from the economical point of view at that time, building a containment for this huge reactor, taking into account all the plumbing for the channels plus the refueling equipment and everything, it would have been like a pharaonic structure. So yeah, I kind of understand the decision here. So that's it for the point 5. And I think it's almost everything I wanted to comment. Here there is something. When the reactor poisoned out, the operators did not shut it down to allow the poison compounds to decay out. Instead, they removed all of the control rods from the core to force the reaction to occur. Well, this is not very precise, because in the way you read this, it seems like they said, come on, this has no reactivity. Let's pull all the rods out to see what happens. It's not like that. The rods are always pulled or inserted following a given velocity, and the main sequence of pulling or withdrawing. So what they did is continue with the main sequence of withdrawal of rods until they reach criticality. The problem is that criticality happened to be just beyond the point of allowable withdrawal. So in this sense, this sentence is more or less true, but it's not like they just withdraw all the rods. At the moment of the accident, there were the equivalent of 7 rods still inserted, which is too few because the minimum was 15 for safety reasons and to keep controllability of the reaction. And finally, what does it say here? Unfortunately, as we started earlier, the control rods are extremely slow in the rbmk, and the graphite water displacer tips actually cause an increase in the core power. Yes, I already commented this. Yes, actually in the previous point I commented both aspects. So one aspect is that the geometry is symmetrical, so the graphite alone at the beginning of a scram doesn't create an increase without the help of other nonlinear effects like positive void. So yeah, here it's a picture of the disaster. And talking about the containment, if a containment could have at least decreased the emission of radioactivity, I don't know, it should be studied for each kind of containment. But as I said, the containment is not designed for an ultimate limit state, so you cannot really expect it to stand this kind of explosion. The top of the reactor building, I think it weighed like 3,000, I'm not really sure, I may say a stupid thing. I don't know if it's 300 or 3,000 tons of concrete, and the explosion just blew it away. So yes, a containment is more sturdy and maybe thicker, but still, it's not made to withstand an explosion. It's just made to withstand 500 kilopascal of pressure, and not dynamic pressure. It's like steady pressure. And also talking about containments, some people discuss if they can withstand an impact of a plane or not. Well, after the terrorism attacks in New York, many people studied this because it's a big concern. And actually, the results are usually non-disclosed to the public. I've been in several conferences in which people studied this with numerical simulations, but they are not allowed to show the results, which makes me think that maybe not all of the results are reassuring. But talking behind the scenes with some people who studied this problem, it seems that commercial airplanes, it's very unlikely that they could break a containment building. And we're talking about containment buildings that were built 20 years ago. The new ones, like the 4th generation PWRs, are already designed to withstand a plane impact. The problem mainly is with jet planes, supersonic military planes, and so on. At hypersonic speed, it seems a dynamic impact in the concrete cannot be taken by the structure. So if we think about some kidnapping of civilian plane by terrorists, it seems it's not a threat for nuclear power plants, at least most of them. It's really unlikely that one of these terrorist attacks could break a reactor building. But with a military plane at supersonic speed, it's more likely that it's possible to break it. So that's some small concern. But anyways, we hope this will not happen. And yes, there is a last thing. There is just an imprecision, but it's not that it was wrong, because at the time there was no the knowledge we have now, because there are many numerical simulations that have been done after the 90s. And this document, I think it's from the beginning of the 90s. So here he's talking about 120 times of the nominal maximum at the moment of the explosion, and 3,600,000 megawatts, which translates to 3.6 gigawatts. This is wrong. 3,600,000 is 3,600 gigawatts. But it seems the numbers are a bit lower with the nowadays estimations. But anyway, this doesn't really matter. So that was all. I just commented pages from 7 to 11 or 12 with some imprecisions. I hope I didn't talk too much. Thanks for listening. See you in the next video. Bye.